Are you aware what is 6 dB rule?
No, sir.
No. So whatever I have discussed yesterday, which is the output SNR in terms of dB, no? This expression. Hope you're able to see.
Yes, sir.
Yeah. So output SNR it is, okay? It is output SNR in terms of dB. What we say it is 1.8 plus 6R. Okay, it is 1.76. We are rounding off it to 1.8. Okay, then 6R. Right. So here, what is R? R is the number of bits used to represent each sample, right? Number of bits per sample, it is, right? So every bit contributes how many dBs? Means if the value of R is 1, I say 1.8 plus 6, right? Yes or no?
Yes, sir.
Yeah. As I said, R is the what? The number of bits per sample, right? Required to represent the desired output SNR, right? Means that see R is the number of bits used to represent the levels or sample values, what we can say. Means each uh, bit which we use for representing the quantization level contributes an amount of 6 dB to the SNR. That is what is known as 6 dB rule. Hope understood. Not saying yes or no. Hope understood this point, why it is called 6 dB rule.
Yes, sir.
Huh? Because output SNR is equal to what? 1.8 plus 6R. Right? I said R is the number of bits used to represent the quantization level. Right? So if means every bit contributes an amount of how many dB? 6 dB to the signal to noise ratio. Okay, that is what is called a 6 dB rule. Okay, so this is the expression for output SNR of the uniform quantizer, right? And yeah, here for different values of L, and we all know how L and R are related, right? L is equal to 2 power R. So as the value of R increases, so when R is equal to 5, so L will be what? 2 power 5, so which is equal to 32, right? So when R is equal to 5, the value of L is equal to 32, because 2 power 5 is 32. So during that time, the value of output SNR, the SNR in dB will be 31.8 dB. Means 6 into 5, right? The value of R is 5 right here. So 6 into 5 is 30. 30 plus 1.8 is 31.8. That way we can cross verify. Hope getting my point?
Yes, sir.
Then when the value of R is 6, so 6 into 6 is 36, right? 36 plus 1.8, that is 37.8. Second one. And 2 power 6 is, you know, it is 64. Then when the value of R is 7, so 6 into 7, 42. 42 plus 1.8 is 43.8. That way I am getting SNR is 43.8 dB. And 2 power 7 is 128 levels. Number of quantization levels are 128. And when value of R is 8, so 8 6 are 48. So 48 plus 1.8, it will be 49.8. And 2 power 8 is 256. So number of quantization levels will be 256. So this is a very important expression what I said, and it has been asked so many times to derive. And even if you are attending core company interviews also, they will ask what is the means the way they ask may be different, but this will be the answer. Means every bit increase to represent the quantization level, how many dBs of SNR it will contribute. So you have to say it is 6 dB. Okay, fine. So with this again, a recap of what we have discussed yesterday. So let me take up the next topic, that is PCM. Okay, pulse code modulation. Yeah. How many have joined so far? Okay, still 19 people have joined. Okay, let me go ahead with this. Yes, Ramya. Ramya, you Kashyap. Not talking. Means simply logged in. Ramya. Rakshita. Rakshita K. I want Rakshita W. Rakshita. Namita. Yes, what about Aditi?
Sir, you.
What I'm asking,
Yes.
I'm just calling your name, you're not saying yes. Now you're saying,
Sir, I was unmuting my mic, sir.
oh, fine. But I hope you all are with me now, or not just logging in and doing something else. If you're not responding when I'm calling you people, then I can understand you're not with me. Yes, Ramya. Okay, Ramya, no doubt she is busy with something else, I think. What about Aditi?
Yeah. Yes, sir.
Fine, fine. Okay. Mm, so still Ramya is not coming to line. What about Karunya?
Yes, sir.
Okay, there. Kuber, Kuber. See, fellow is not there, no doubt. Yes, Vishal. Vishal?
Yes, sir.
Yeah, can you tell me what is the 6 dB rule, man? I've heard 6 dB rule.
I don't remember.
You don't remember. Just now you joined, huh? I think before I
Yes,
come
sir. I
back
joined just now. I joined.
just now, I repeated that. What is 6 dB rule? What is the expression for output SNR
So
and all
output
the.
SNR is 3 by 2 into 2 per hour.
Ah,
In decibel,
yeah.
it is 1.8 plus 6 hours, sir.
Yes, yes. Whatever is displayed is this one. This is the output SNR expression in terms of, right? And
Yes,
this
sir.
is the expression for in terms of dB.
Yes, sir.
So I repeat once again why it is called 6 dB rule, because here see R is the what number of bits per sample, right? R is the number of bits used to represent each sample, right? When R is 1, it contributes 6 dB, right, to the SNR. So when like that. So that is why it is called 6 dB rule. Okay, means every bit, each bit which we use to represent representation level or quantization level contributes to the amount of output SNR of 6 dB. Hence, it is known as 6 dB rule. Already I told this table, okay, how we get and all. Okay, fine. So let me go ahead with this. Let me take up the next very important topic, that is pulse code modulation. Okay, this pulse code modulation is one of the basic form of digital pulse modulation. Okay, so what we do in PCM is the message signal will be represented by a sequence of coded pulses. Okay, message signal will be represented by a sequence of coded pulses. Okay, how do we do that? We do that by representing the signal in discrete form, that is in both time and amplitude. Means, hope you are understanding what I want to say. In PCM, the message signal is represented by a sequence of coded pulses. So, how do we achieve this? How do we represent the message signal by a sequence of coded pulses, right? So, that is done by representing the signal in discrete form, that is in both time and as well as amplitude. Means time and amplitude means what? I need to do sampling, then I can make the signal discrete in time. Then if I do the quantization, then means if I discrete the amplitude, then I can say the amplitude is discretized, right? So that is a quantization process. So what I wanted to say here is the basic operations performed in the transmitter of the pulse code modulation system are sampling, quantizing, and encoding. So these are the three basic operations performed in PCM transmitter. So clear? Sampling, quantization, and encoding. Okay. So what we do in PCM, I said, a message signal is represented by a sequence of coded pulses. How do we achieve that? We do that by representing the signal in discrete form in both time and amplitude. So these are the three basic operations performed in the transmitter of the PCM, I said, that is sampling, quantizing, and encoding. So same thing, I described that in the form of block diagram. So this is my analog signal. I give that as an input. First I do sampling, right? So when I do the sampling, I am going to discretize the signal in time. So if you take this x-axis is time, right? So I'm going to discretize the signal in time. Then the next step is quantizing. So actually it should be like this. Okay, quantizing means, isn't it? I'm going to discretize the amplitude. Okay. So this is the quantization. Then I do the encoding. Means each quantized level, I will be representing it by binary number. It may be any other number also. So I'm representing it by binary numbers, right? So I get the means that binary encoded wave, signal will be represented by a pulse. That may be binary pulse or any other pulse. So in that way, I get the digital data. Hope this point is clear. So this is sampling, quantizing, encoding. All these three steps together is known as the PCM encoder. Hope is this point is clear. So when I do the sampling, I get PAM signal. You all know that, right? Means when I discretize the signal in time, I get PAM. Then I do the quantization. Means I'm going to discretize the signal in amplitude, right? Then I do the encoding. Means each represented level will be represented by some numbers. That number will be encoded by a binary pulse user. In that way, I get the digital data. So to have better understanding, let me take the example. So this is one example which I can show. Right. So this you can take it as time. Okay, x-axis, and y-axis will be the amplitude. So this is my analog signal. So whatever the dashed line is there now, so this is my analog signal. Okay. Okay. So this is my analog signal. I hope it's already written. I need not write again once again. So dashed line, right? I think I will complete this and I will. Yeah. So this is my analog signal. So it's already shown here, the dashed line. Then see, this is my sample value, right? The thick line, vertical lines, they're the sample values. And then another dashed line, this will be the my representation levels. Okay. So here I am representing as a 0, 2, 4, 6, 8 like that. Okay. Yes, if this point is clear.
Yes, sir.
So here I have 8 representation levels. Means I can use 3 bits to represent 8 representation levels. That is from 3 zeros. Okay, 3 zeros to 3 ones. Right. That is from 0 to 7. That will give you the value of 8 sample, 8 levels. Right. From 0 to 7. Yes, is this point is clear? I'm asking.
So
So
which are
I said very, very important.
Sir,
Yeah.
it said we'll make pulses, no, sir. So, which are the pulses?
Yeah, I will tell that pulses means, yeah, first step is sampling, then second step is the quantization, the third step is encoding, right? After encoding, each of these binary numbers will be represented by a pulses. So we call that as a line codes. There are different types of line codes. I will discuss about that. Okay, means I can represent 0 by no pulse and 1 by a pulse having some width. Na? So like this I can represent, right? So this is my 0. This will be 1 I can represent. I can represent 0 by no pulse and 1 by a pulse having some width and magnitude, right? Then again it will be 0. So it will, I can write 0, 1, 0 like this. Hope understanding what I am saying. Yes, Naurin.
Yeah, sir.
Yeah, I have example also. I will show that. Yeah.
Okay.
So this is again a little bit more in-depth understanding about the entire process of PCM. Okay. So what is this? This is my analog signal. Okay. Whatever is shown, this is my analog signal. So here, of course, I have not shown the sample sampling this one. Means the sample values are shown here. So these are the sampled values. First one, right? So this is minus 0.2 volts, first point. Then this will be minus that is 0.1 volt. Hope understanding my this one. So this is the minus 0.2 volts. Okay. Next, this one is 0.1 volts. So next, this one is what? This point. This sample is minus 1.1 volt, right? Then this will be, this sample is 0.8 volts, 0.8 volts, right? Then this one will be 0.6 volts, like that. Okay, so these are the sample values. Then see quantization, quantized values I'm saying here, right? Quantized values. So the entire peak to peak signal has been divided into 8 levels, starting from 0 to 7. So these are the level number. Okay, of understanding 0 to 7. Then I represent this amplitude. So if I start from here, so 0 volts, right? Then 1 volt, 2 volt, 3 volt, 4 volts. So there is a peak voltage. Similarly, the negative side 0, minus 1, minus 2, minus 3. Then it will be minus 4, right? So what I am doing here is I am taking in between steps. I hope you understand. Yesterday I discussed, right? MK, then MK plus 1. In between value will VK, right? So that will be my quantized level, isn't it? Yes, are you getting my point?
Yes, sir.
MK, just if you have remembered that MK, then VK wrote, then MK plus 1 I wrote. So for MK to MK plus 1, in between sample value, right? Middle of the dot is the VK. So that is my what quantized level. So here the quantized values are these things. Means 0 and 1, so 0.5. Then 1 and 2, 1.5. Then 2 and 3, 2.5. Then 3 and 4, 3.5. Okay. So these are my quantized values.
Sir,
0.5 on.
sometimes you're this thing rounding off higher, sometimes you're rounding off lesser, no, sir. Why is that?
Yeah. Means why it is rounding off to the nearest level. Nearest level. So here it has means if the sample value is minus 0.5, no? Right? Means it is just below, I think, below 0. So it is minus 0.2.
So,
Right? So it
like,
is rounded off to minus 0.5.
see, like,
That
for
is the
example,
nearest
see,
value for this.
yeah, I understood that. See, the second last one is minus 2.2, right? You rounded it, like, you quantized it to minus 2.5. Whereas the previous one is minus,
This one,
the second last one, so.
second last. Okay. This one minus 2.2.
Yeah, it's minus 2.5. Whereas
So
the
minus
previous
2
one is
point.
minus 0.9, but you quantized it to minus 0.5. Should have quantized it
This
to
minus
minus 0.5.
2.2 is nearest to the minus 2.5 only. No, for this it is nearest.
It's nearest to
Oh,
2,
this
sir.
one. This point, minus 0.9.
Sir, like, you've done both. Like, you've just one you rounded it up, one you rounded it down. That's what.
Okay. Mm. Okay, so minus 0.9 is there, that has been rounded off to minus 0.5. Yeah, even minus 0.8 is rounded off to minus 0.5. Okay, then minus 2.2 has been rounded off to minus 2.5. Okay, then this is 2.6 that has been rounded off to 2.5. Yeah, hope this
ಸರ್ ಅದು 0.9 ಇರೋದನ್ನು 0.5ಗೆ 2.2 ಇರೋದನ್ನು 2.5ಗೆ ಅಂದ್ರೆ ಮೇಲೂ ರೌಂಡ್ ಆಫ್ ಮಾಡಿದೀರಾ ಕೆಳಗೂ ರೌಂಡ್ ಆಫ್ ಮಾಡಿದಾರಲ್ಲ ಸರ್ ಅದು ಹೆಂಗೆ
okay, your doubt is that, so since here it is minus 0.9, you would have taken it to minus 0.5, right? You have taken to minus 0.5. You are expecting it can be done for 1.5 also, minus 1.5 also.
Yes, sir.
But if I round it off to minus 1.5, error will be more, no? Understanding? See, nearest is minus 0.5 only, na? For minus 0.9. If I rounded it off to minus 1.5, then minus 0.6 will be the difference. But when I rounded off it to minus 0.5, only difference is minus 0.4. So error will be less, na?
Yes, sir. Yes, sir.
Getting my point in that way. So always we rounded off to the nearest sample value. Okay, nearest foundation level. So I hope this point is clear. So entire input signal is divided into different means here the positive amplitude of the signal is 4 volts and negative amplitude of the signal is minus 4 volts, right? So you have understood how we have divided this, right? That is totally 8 levels, that is from 0 to 7. Then now I got the quantized values also. We take in between of these amplitude levels, right? And then how do I encode that? Means from 0, I can write 3 zeros, right? With 8 levels are there. I can use 3 bits to represent each of these decimal number in binary, right? So 3 zeros to 3 ones. That will give you 8 number, right? 0 to 7. Is that point is clear? So I need not write here 0 in binary. You know how to write 3 zeros. You write, right? Then 1 will be 0 0 1. Isn't it like that? 2 will be 0 1 0. Isn't it? 3 will be 0 1 1. 0 1 1. Then 4 will be 1 0 0. Okay. 5 will be 1 0 1. 5 will be 1 0 1. Then 6 will be 1 1 0. Then 7 will be 3 ones. So based on this, see, based on the level number, say I am writing the level number based on the quantized value. See, for minus 0.5, my level number is 3. So that is why it is written here 3. Then for 0.5, my level number is 4. So that is why it is written 4 here, right? Level number. Then for minus 1.5, the level number is 2. That is why 2 is written here. Then for 0.5, right? Next is 0.5. For 0.5, level number is 4. That's why 4 is written. Okay. Then next 0.5 is there. Again, the level number is 4. Then for minus 0.5, the level number is 3, which is written here. Then for minus 0.5, again, level number is 3. Then for minus 2.5, the level number is 1. The level number 1 is written. Then for 2.5, the level number is what? 6. Right, 6 is written. So now I am going to write the binary equivalent of that. Okay, for 6 it is 110. Hope you understand. Then for 1 it is 001. For 3, 0111. Then again 0, 311. 4 it will be 100. Yes, 4 again 100. 2, 010. 4, 100. Then 3, 011. So how do I represent this in terms of waveform, right? So 0 by no pulse, 1 will be a pulse, right? Yeah, this also you can understand, or first I will tell this one. So these are my digits, right? Here I have taken for 0 to 15 means 16 levels. I can represent each digit with 4 binary numbers, right? 4 zeros to 4 ones. So here 0 is the same one DC line I have written. Next 0001, right? So only represent 1 by 1 pulse. Rest other 3 things are by no pulse. Then 0010. So For 1, I am getting 1 pulse. This will be my 1. Then here 2 zeros, then here 1 0, right? Hope understanding this point. Then 0 0 1 1. So 2 zeros by no pulse, then 2 ones by 2 pulses, right? So like this I can represent each of this binary number with the waveform. Okay. Yeah, this is another example which I have taken for just explaining the PCM. So this is my analog signal. Then here I do the sampling, right? At T, 2T, 3T, 4T, 5T, and so on. I have samples. Then after sampling, I will be doing the quantization. Then each quantizer level will be represented by a number. Then I am based on the sample value, right? And its code, I will be representing this waveform. Right? Is this clear? So this one example will be more than enough for you to explain what PCM is. So you can take any random waveform of M of t, you sample it, quantize it, represent the number of levels and its quantized value. Then you can write its nearest sample value by rounding off it to the nearest quantized level. Then its equivalent binary code. Yes, if you have any doubts, you can ask about this. Yes, in addition to that, one more example where you can understand about this PCM encoding process, right? Yes, have a look, try to read by yourself, understand. So here 8 levels, I already said what is its equivalent binary number, right? So this is at the receiver side, okay? This is for reconstruction. So this is at the transmitter side. Hope you will be able to explain this by taking any example, right? So by this time, you know what are the basic operations involved in PCM. Anyone can say what are the 3 basic operations involved in PCM at the transmitter side?
Sampling, quantization, and encoding.
Yeah, good. So sampling, quantizing, and encoding. So these are the basic operations involved in the transmitter of the PCM. Yeah, one more example I am showing. Hope here the number of levels are 16. Okay, so that is why it is represented by 4 binary digits. That is 4 zeros to 4 ones. Okay, so this sample is 1 triple 0. That is 0th level, right? Then this will be 0. It is 1, 2, 3. Third one will be 1 0 1 1. So that is why it is. First one is 1 3 zeros, right? 1 3 zeros. Next level is what? This sample. Right? Next sample is this one. That is 0 1 2 3. Means for this one 3. That is what is this number? 1 0 1 1. Okay. So 1 0 1 1. So this is a waveform is written. So for 1 represented by pulse, 0 no pulse, then 2 ones with the 2 pulses. The next sample is this one. That is what? 0, 1, 2, 3, 4, 5, right? And its binary equivalent is 1 1 1 0 1. So this number. So 1 1 0 1 here. Okay. So for that, 2 pulses, then 0 1. Like
Sir,
that it is written.
After 1, why is it going to 0, sir? Okay.
See 1 0.
Like, does it have to go to 0 after every sample?
No, not every sample. See, this is my first sample, right? That is 0th level. I represent by 1 triple 0. That is why first pulse is 1. I represent by a pulse. Then 3 zeros are there. So no pulses. Next, what is sample value? Here it is there, right?
Got
its
it.
equivalent
Thank you,
binary
sir.
number is what? 1011, right? So 1011 is written. So again, 1 represented by a pulse, 0 no pulse, then 2 ones will be represented by 2 pulses.
Got
Getting
it,
my
sir.
point?
Yeah, got it, sir.
Yeah. Next is what? This one. So that is represented by 4 ones. So 4 ones. Right? Yeah, here see 3 samples with the same number. 777. Okay. Then again it is 5, then it is 3, this number 5, 3, then again this will be 0, right? Then this point is -3, then this point is -6, and again this point is -8, these 3 points. That is why 3 -8 is written. So for that equivalent number is 3 zeros, that is why no pulses only here, right? 0, 0. So beautifully you can explain the concept of PCM by taking the example like this. So here everything is shown, even sampling interval also, right? Yes, shall I go to the next slide?
Yes, sir.
Yeah. Yeah, this is one application what I wanted to say about PCM. It has many applications. Okay. We'll have a discussion about that also. Basically, it is used in telephone, right? For transmitting our voice signal. So as I said, our voice frequency range is from what? 300 Hertz to 3400 Hertz, and it will be rounded off to 4 kilohertz. So as per Nyquist rate, it will be sampled at twice the highest frequency of the message signal, right? So we get 8,000 samples per second. Okay, 8,000 samples per second. Then here the quantized values are what? 256. Means how do I represent audio? Okay, by using this. That is the example. So 256 means what? It is 2 power 8, right? Is it so? Yes, 2 power 8 is 256. So with that, I need a bandwidth of 64 kbps. Okay, that is 64,000 bits per second. Per second, I will be able to transmit 64,000 bits. So this is all about the transmitter side. For the receiver side, again, it will do the reverse process, right? So similar to that, other examples means in CD, okay? In CD, it will be at this rate, that is 1.411 Mbps. Okay? And for MP3 player, okay, for MP3 player, so these are the different rates. That is, one is 96 kbps, another one is 120 kbps, and third one is the 160 kbps. Okay, so there are 3 different rates can be achieved with the MP3 player. And for internet telephony, okay, so this is what the band achieved, that is 4.3 kbps and up. Yeah, so I think these examples will be more than sufficient to understand about PCM. So whatever I am saying here now, theory is about already you know, because we know what is sampling, right? So before we do the sampling, we pass the signal through a pre-aliasing filter, right? That is basically a low pass filter, and we know why we pass the signal through that pre-alias filter, okay, to make the signal strictly band limited, so that we can avoid aliasing in the recovery of the message signal, right? So there is a point which I have written here. The low pass filter prior to sampling is included to prevent the aliasing of the message signal. Then the quantizing and encoding operations are performed in the same circuit. So that is why it is known as analog to digital converter. Okay, so PCM is nothing but analog to digital converter. So this is all about transmitter, as I said. Then at the receiver side, we do the what? The reverse operation. So the basic operations done in the receiver are what? Regeneration. Okay, means we use a regenerative repeater between the transmitters and receivers so that we can transmit the signal for a longer distance. Let us see what is the block diagram of regenerative repeater and all. So this we do the regeneration of the impaired signal, means as the signal is transmitted to the channel, the noise will be added to that, right? So we do the regeneration, then do the decoding, and then we do the reconstruction of the train of the quantizer samples. So these are the steps involved in the regeneration and decoding at the receiver side. Okay. So as I said, regeneration, right, occurs at intermediate points. Okay, the purpose of regenerative repeater is to extend the range of communication. Okay. Just I will show the block diagram of that. Yeah. Yeah, fine. So anyhow, we will not be transmitting a single signal, a single message. We do the time division multiplexing and transmit several signals over the common channel. And as we all know, in the TDM, we need to have synchronization between transmitter and receiver, that is commutator and decommutator, right? Then only it is possible to get back the proper signal at the receiver side. Yeah, so this is what the block diagram of your PCM system, which I've already told. So the incoming signal, that is my continuous time message signal, right, will be passed through a low pass filter. I said what is the purpose of that, right? The purpose of this low pass filter is to make the signal strictly band limited so that we can avoid the aliasing. After that, it will be sampled, right? Then, so by doing sampling, what we can say, we are going to discretize the signal in time domain. Then we do the quantization, means we are going to discretize the signal in amplitude also. Then we do the encoding. Okay. So after encoding, we get the PCM signal that will be applied to the channel. So these are the steps involved at the transmitter side. Then along the transmission path, as I said, we are using the regenerative repeater. So this regenerative repeater will be again doing the means it will again reconstruct the signal. Okay, because as it as the signal passes through the channel, I said it will be getting distorted due to channel noise. So that a distorted PCM signal will be given as input to the regenerative repeater, right? Then it does the regeneration of the signal. Then it will be transmitted further. So we can have n number of regenerative repeaters along the transmission line, along the transmission path, to extend the range of communication, as I said. So this is about the receiver side. So in receiver, what we do is first there will be a regenerative circuit, right? Then the decoder, it does the decoding of the operation. Then there will be a reconstruction filter to get back the original signal. Then that will be applied to the destination. The destination may be your speaker and any other thing, right? So these are the different steps involved in the receiver side. So these three block diagrams are together what we call as a PCM system. Transmitter, then transmission path, then the receiver. Okay. So again and again, I did not again discuss about what is sampling, what is quantizing, what is encoding and all. since I've taken one example and I've shown all these 3 steps, I think you should be able to write by yourself. This is a theory, what I've just said so far. Want you can read out as a recap, right? Means what I mean to say is already we know what is sampling. Yes, anyone can say what is sampling? Sovik, can you say what is sampling? Sovik Roy? Yes, Tipana. Tipana is there. Yes, Manusri, can you tell me what is sampling? Manusri. Manoj? Yes, Pooja. Yes, Ananta. Yeah, Manusri, what you are
Hi.
taking so much of time?
Uh, so discretization of analog signal in time is sampling.
Okay, discretization of analog signal in time. Okay. Yeah, why do you do that? Why you want to discretize the analog signal in time?
To get discrete signals, sir.
Fine, what is this purpose? It is written here. See, first, second, third, they're all the known things, right? We said the message signal will be sampled with train of narrow rectangular pulses. With that, we will be able to approximate the instantaneous sampling process, right? So, in order to ensure perfect reconstruction of the message signal at the receiver side, we do the sampling and we take the samples at greater than what's the highest frequency component, right, of the message signal. And I said that before we give a signal to the sampling, we pass it through a low pass filter, which is there at the front end of the sampler, right, to exclude any frequencies higher than or greater than WHz, right, to avoid the aliasing. So, by doing so, what happens? This sampling permits the reduction of the continuously varying message signal to a limited number of discrete values per second. Okay. By
Yes.
doing sampling, I will be able to represent with a limited number of discrete values per second. Okay.
Yes, sir.
Yeah. Because the analog signal is continuous in time, means it will have infinite number of, means it exists for infinite duration, right? So I wanted to make it that as discrete. Means by doing sampling, I will be able to say, yes, these are the number of samples per second with so and so values. Yeah. So that is the first step. Then what is the second step? Second step is the quantization, right? I think, yes, Namita, can you tell purpose of quantization? Namita.
Yes, sir.
Yeah, can you tell the purpose of quantization? Already we have discussed yesterday, right? What is quantization? What are the different types of quantizers and all? And even we have derived the expression for output SNR and all. Just as a recap, can you just say the purpose of quantization?
Sir, like when we discretize the analog signal, that's sampling, sir, but like quantization.
Okay, when I sample it, it becomes analog signal becomes discrete in time. Why do I go for quantization? What the quantization process will do?
Sir, like because you have to map the continuous values, no, sir, that's why we.
No, what the quantization process will do? Is it going to discretize the amplitude of the signal? Namita.
Yes, sir, like the amplitude of signal only it will discretize, sir.
So when I sample it, it becomes, means analog signal becomes discrete in time, right? But still its amplitude is continuous. To make the amplitude discrete, I do the quantization. After that, I will be doing the encoding, right? So while I said about the quantization, there are two types of quantization. What are those two types of quantization? First is uniform and non-uniform quantization, right? What happens in uniform quantization? What happens in non-uniform quantization? Then under uniform quantization, again there are two types. One is mid-trend type quantizer, another one is mid-rise type quantizer. Yeah.
Sir, uniform quantization means like there will be equal spaces between the
Yeah.
discretized amplitudes.
Yeah, representation levels will have equal spacing. Right, in case of non-uniform quantization, the representation levels will have a different spacing. So there is a difference. Fine. Since, as I said, in uniform quantization, the representation level, the spacing between the representation levels will be fixed, right? But in some applications, it is required to use the variable separation between the representation levels. Okay, say for example, voice only. Okay, here the range of voltages covered by the voice signal will have peaks of low talk to the weak passes of weak talk, right? Means sometimes we talk with high pitch and sometimes we talk with low pitch, right? So there will be variations in its magnitude, right? So that variation will be in the order of 1000 to 1. In that case, I need to vary the spacing between the adjacent representation levels. So we use non-uniform quantization for voice signals. Okay. Hope that is clear. So I am talking about now non-uniform quantization. In the previous class, we have discussed about uniform, right? Uniform quantization. In that, what is mid-rate type and mid-range type and all. So I said the purpose of non-uniform quantization, right? Because for voice signal, the range of voltages, okay, will be varying, right? That depends on what? Depending upon the peaks of the loud talk to the weak passes of the weak talk, right? Means there will be variation in our speech, right? Sometimes we talk loudly, sometimes we talk with low pitch. So with that, the variations will be in the order of, you say it is 1000:1. So because of that, we need to have the variations in the separation between the representation levels. So that is known as the non-uniform quantizer. Okay. So with that feature, in the non-uniform quantizer, the step size will be increasing, right, as the separation from origin of the input-output amplitude cache is increased, right? In case of uniform, the step size is fixed. As I said, the delta, if it is 1 node, it will be increasing in terms of 1 node only. But in case of non-uniform quantizer, the step size delta will be keeps changing. Okay, that depends on the spacing between the adjacent representation levels. Okay, means I will be representing the large amplitudes with a large step size and small amplitudes with small step size. So the large end step of the quantizer can take care of possible excursions of the voice signal into large amplitude ranges, right, that occur infrequently. Similarly, the weak passages which need more protection are favored at the expense of the loud passages, right? So a nearly uniform percentage precision will be achieved throughout the greater part of the amplitude range of the input signal, right? So with that, it results a few steps which are needed than would be the case if the uniform quantizer is used. Okay, if I use a uniform quantizer, I may need more number of steps to represent that particular signal. But by doing this non-uniform quantizer, I will be able to represent the entire peak-to-peak signal with a few number of steps. So that is the great advantage of non-uniform quantizer. And this is the formula which we use for finding the non-uniform quantization level, right? So the use of non-uniform quantizer is equivalent to what? Passing the baseband signal through a compressor. Okay, and then we apply the compressed signal to the uniform quantizer. So non-uniform quantization means it is as good as equivalent to passing the baseband signal through compressor and then applying the compressed signal to the uniform quantizer. So there is a law known as mu law. Okay, this is known as the compression law, we say. A particular form of compression law which is used in practice is known as mu law. And that mu law is defined mathematically like this. That is V of mod is equal to log of 1 plus mu into m, mu into mod of m divided by log of 1 plus mu. Okay. So let us see how the graph will be looking like that and what is this V and m and other things. So mu law will be defined like this. P mod is equal to log of 1 plus mu into mod m divided by log of 1 plus mu. So since it is logarithmic, I hope we will be able to understand how waveform will look like. Right? Yeah. So here M and V are the normalized input and output voltages. Okay, V is the output voltage and M is my input voltage, and they are normalized. And the value of mu will be a positive constant. Okay. Okay, I will come back to that figure, how it is plotted. Okay, for different values of mu. So for uniform quantizer, the value of mu will be 0. Okay. So the derivative, that is d by, this is a message signal, right? M is my input signal, V is my output signal. So derivative of that will give you log of 1 plus mu divided by mu into 1 plus mu into mod m, right? So here the mu law will be strictly linear nor strictly logarithmic. I will show that graph. how does it looks like, but it is approximately linear at low input levels, okay, corresponding to this, that is mu into mod of m is much less than 1, and it will be approximately logarithmic at high input levels, that is which corresponds to mu into mod of m is much greater than 1. Okay. So mu log is neither strictly linear nor strictly logarithm, right? I said at low input levels it is linear, and at high input levels it is logarithmic. Okay. Yeah, I think better I will show the diagram of mu log, then I will come back to this equations. Yeah. Said now, when mu is 0, hope you are able to understand this. This is x-axis is normalized input, that is m, right? X-axis is normalized input and the y-axis is normalized output, b. So input versus output I am drawing. So it is linear. When mu is 0, it is linear, means it is a uniform quantizer, isn't it? So for different values of mu, this will be the curve. When mu is 5, I get curve like this. Okay. So as I said, at low input levels, it is linear, and at high level inputs, it will be logarithmic. I hope we will be able to find that curve. Then when mu is 100, it looks like this. Right? At low input levels, it is linear. At high input levels, it is logarithmic. So this is a mu law graph. Similarly, the another one is there, that is A law. Okay. So when A is 1, it will be a linear, this one means it will be a uniform quantizer. So when A is not 1, then it becomes non-uniform quantizer. Okay, so this is for A is equal to 2, and this is for A is equal to 100. So these are the two compression laws which are used in non-uniform quantization. Yes, let me, I hope you could grasp this picture. Mu law and A law. Yes, for different values of mu. Okay. Yeah, rest of the things I will discuss, I think, in the next class. Okay. I think with this, let me stop.